Hi there, Algebra 2. Here we go into lesson 3. Now we're going to be working with logarithmic functions. They're basically going to be the opposite of exponential functions. Here we go. So here's our basic exponential function. Here's our basic logarithmic function. A logarithm is going to be how we undo an exponential function, or in other words, how do we solve for x in an exponential function? The logarithm will help us do that. So thinking about solving a regular old equation over here, notice that we keep doing those inverse operations to solve it. The logarithm is the inverse operation of an exponential function. The way that we read this, we would say that the log base b of a is x. B is going to be the base. A is going to be the number we're taking the logarithm of, and then x is our answer. One thing to note here is that the answer x is going to be the exponent. It's the exponent over here. So it doesn't look like an exponent anymore, but that's what it really is. It's the exponent of this base. Here's your reference over here. We're going to take an exponential equation and rewrite it as a logarithm. So the first one is going to be log base 3 of 243 equals 5. And again, what this means is that 3 to the 5th power equals 243. That's what we have right here. This is just the inverse operation to have your answer be that exponent. This next one is going to be log base 25 of 5 equals 1/2. The next one's going to be log base 10 of 10,000 equals 4. The next one should be log base 6 of 1/6 equals -1. If this 1/6 doesn't show up on your notes, just add it in there. And then the last one is going to be log base a of c equals b. That's not the same letters as they use up here. They're just trying to make sure you understand where all those pieces go in a logarithm. In this first one, I'm going to rewrite from the logarithm to the exponential. 9 to the 1st equals 9. Your base is this number right here. The value at the end is the exponent, and then it equals this number right there. The next one we can rewrite as 2 to the 9th equals 512. The next one can be written as 8 to the 1/3 equals 2. The next one can be written as 4 to the -2 equals 1/16. And the last one can be written as b to the 0 equals 1. And here's something interesting. Any number to the 0 power is going to equal 1. That might come in handy every now and then. This table from your book is just reminding you of a few things that you already know with exponents, like a number to the 1st power is that number, a number to the 0 power is 1, and they're just showing you what that's going to look like in a logarithm. Another exponent property you're going to want to review is that anything to a negative exponent makes it into a fraction, and it ends up in the denominator with a positive exponent. So for example, 4 to the -2 is the same as 1 over 4 squared, or 1/16. We're going to evaluate some logarithms here, and the first thing is that if there's no logarithm number or base written, then we're going to assume it's base 10. It's kind of like when you have just x, you know that there's a 1 in front of that x. So what we have to think about here is 10 to what power, because that's what the logarithm equals as an exponent, equals 0.01 or 1/100th, and it might help us if we write it as a fraction. So I noticed that it's going to be -2 because 10 to the -2 power would be 1 over 10 squared, which is going to be 1 over 100. In number 2, I'm thinking 5 to what power is 125, and I realize that that's going to be 3. 5 to the 3rd power is 125. In number 3, I'm thinking 5 to what power is 1/5, and that's going to be -1, because that's what's going to make it into a fraction and put it in the denominator. In number 4, this is a base 10, so 10 to what power equals, and this is the same as 1/100,000, so I'm just going to rewrite it like this. And I would see that that exponent would need to be negative 5 because 10 to the 5th is going to be 100,000, but it needs to be negative to make it go into the denominator. In number 5, 25 to what power gets me 0.04, which is 1/25th. And so that would also be negative 1 because that's what's going to make it into a fraction with 25 in the denominator. So the logarithm, again, is the inverse function of the exponential, which means that when you graph them, they're going to be reflections across this line, and this is called the line y equals x. And also the domain and range are going to be switched when you go from an exponential function to a logarithmic. Here's what it would look like if I graph those points. I did change the scale on my graph just a little bit, just so my points are a little more spread out. When we look at the inverse, remember the logarithm is going to be the inverse of our exponential function. It's going to be log base 1.25 of x will equal our f of x. Now again, we're not going to do this in a calculator yet with a logarithm, but we know that when we take an inverse, we just flip our x and y values. And so this will be 0.64 comma negative 2, 0.8 comma negative 1. When you graph the inverse, it'll look like this. And just like with any inverse function, the graph is going to be the reflection across that line y equals x. And so we can see that it is reflected. For the domain and range, let's graph them on Desmos so we can get a better picture of what this looks like. For domain and range, looking at our blue one, this is our original 1.25 to the x. We can see that the domain is the x values. That's going to be all reals. The range for our y values looks like y can only be greater than or equal to 0 because it looks like our x-axis here is the asymptote. That line gets close to it but never touches. Going to our inverse function, the red line, our domain, it looks like it has to be x values being all positive because we have an asymptote here where the y-axis, the function gets closer to the y-axis but never touches it. So the domain is x is greater than 0, and our range, our y values, is going to be all reals.